All right, let's jump right into a classic rivalry, a real chemical showdown. In one corner, you've got raw, brute strength, and in the other, you've got steady, dependable reliability. This isn't just a fight in a beaker, it's a fundamental choice chemists have to make, and the winner really tells us a lot about what matters most in the lab.
So here's the problem every chemist faces. Imagine you've got a glass of water and you dissolve some salt in it. The salt disappears, right? It's completely invisible. But what if you need to know exactly how much salt is in there? Not just a guess, but the precise amount. How in the world do you measure an ingredient you can't even see?
Well, the solution is this beautiful, really clever technique. It's all about using a chemical that you know everything about to figure out the mystery of one that you don't. You can think of it like a form of chemical accounting, where every single drop tells you something important.
Now, the fancy name for this process is redox titration. I know, it sounds a little technical, but the idea behind it is actually pretty straightforward. It's basically a carefully controlled chemical reaction, almost like a chemical handshake, where electrons get passed from one substance to the other. And by keeping a close eye on that exchange, we can get an unbelievably precise measurement. This is the battlefield for our two main contenders.
Okay, first up, let's meet our reigning champion, dichrometry. This technique is built around a bright orange compound called potassium dichromate. This stuff is the definition of a trusted workhorse. You'll find it in labs all over the world because, well, it just works.
And using it is wonderfully simple. You get your mystery solution ready, you add a little bit of acid to get the conditions just right, and then you start adding the potassium dichromate, drop by drop by drop, and you just watch and wait until, bam, you get a sudden, sharp color change. That tells you the reaction is done. That's your endpoint. It's clean, it's simple, and it's incredibly accurate.
But what is it that makes this stuff so incredibly reliable? What's its secret? Well, it has a kind of chemical superpower, a quality that makes it a chemist's absolute best friend. It's called a primary standard. And trust me, understanding this one little concept is the key to this entire showdown.
So what on earth is a primary standard? Okay, imagine this. You need a weight that is exactly 1 kilogram. You could go outside, find a rock you think is about the right size, or you could use a certified, perfectly calibrated 1 kilogram metal block. That block is the primary standard. In chemistry, it means potassium dichromate is so incredibly pure and so stable, you can just weigh out a specific amount, dissolve it in water, and you know its concentration. Exactly. No doubt, no guesswork.
But hey, what's a champion without a challenger, right? So let's bring in the rival, permanganometry. This technique uses a really vibrant, deep purple chemical called potassium permanganate. And let me tell you, it's flashy, it's powerful, and at first glance, it looks like it should be the better tool for the job.
And if you just look at the raw power, it is stronger. This chart shows what chemists call oxidizing strength. Look at those numbers. Permanganate comes in at 1.51 volts, which is quite a bit higher than dichromate's 1.33. That's way more chemical horsepower. It should be able to react faster, more forcefully. It should be better. Which, of course, brings up the big question. If it's so much more powerful, why isn't potassium permanganate the undisputed king of the lab? Why don't people reach for it every single time? Well, it turns out that with great power comes great fussiness.
And here's the laundry list of problems. First, it's not pure, so you can't just weigh it and know its strength. Then, its solutions literally fall apart over time, and they decompose when they're exposed to light, which means you have to store it in special dark bottles. And to top it all off, a lot of the time you have to heat everything up just to get it to work right. It's powerful for sure, but man, is it high maintenance.
So let's put them side by side, our direct head-to-head comparison. This is where those practical day-to-day differences really start to jump out.
It all starts with purity. With dichromate, you weigh it, dissolve it, and you're ready to go. It's a primary standard, but with permanganate, it's what we call a secondary standard. You have to standardize it first, which means you have to run a whole separate experiment just to figure out its true strength before you can even start the experiment you actually want to do.
And then there's stability. You can make a dichromate solution, put it on a shelf, and come back weeks later, totally confident that its concentration hasn't changed one bit. A permanganate solution, though, it starts degrading almost right away. The solution you use in the morning might actually be weaker by the afternoon, and for a scientist, that's an absolute nightmare for getting reliable results. And finally, there's just the day-to-day reality of working with them. Dichromate is easygoing, it's not sensitive to light, it works just fine at room temperature. Permanganate is a total diva.
It demands special dark bottles to protect it from the light, and like we said, you often have to bust out a hot plate just to coax it into reacting properly.
So when you lay it all out like this, the picture becomes crystal clear, doesn't it? I mean, sure, permanganate wins on that one metric of raw power, but dichromate just sweeps the board on every single practical measure that matters in a lab: purity, stability, and just general ease of use.
So for the vast majority of jobs that need to get done in a working lab, day in and day out, we have a clear winner. And the victory doesn't go to the strongest chemical. It goes to the most reliable one.
And this quote right here just sums it up perfectly. In science, especially in this kind of analytical work, consistency and reliability are everything. You have to be able to trust your tools and trust your results 100%. And that's why the sheer dependability of potassium dichromate makes it such an invaluable champion for everyday lab work.
Okay, so this has been a fun chemical showdown, but why does any of this matter outside of a chemistry lab? Where does this reliable technique actually make a difference in the real world?
Well, one of its most critical jobs is measuring iron. And think about that for a second. We're talking about everything from the quality of steel beams used to build a skyscraper to the exact amount of iron in a vitamin supplement you might take. Titrometry provides that critical, precise measurement needed for quality control. It's the quiet, reliable process that helps make sure the bridge you drive over is strong and the medicine you take is safe. It's all about getting it right every single time.
You know, this whole showdown between raw power and quiet reliability, it's a theme you see everywhere, not just in chemistry. And it really leaves you with a final thought. What other invisible but vital ingredients are chemists uncovering right now with tools just like this? What other powerful but fussy options are being set aside for something a little quieter but a whole lot more dependable? It really makes you wonder.